In the beginning, there was no dawn, no sky, no horizon, only a singular eruption of light and matter, a universe expanding from nothing into everything. The Big Bang, our origin, our first moment, or so it seems, but hidden beneath this birth, cry of creation, there is a stranger rhythm, a pulse, faint yet enduring, a ticking that may have preceded the very act of creation, like a heartbeat before the body, like a shadow cast before the flame. Physicists peer into the fossil glow of the cosmos, the cosmic microwave, background searching for patterns, and there, across the static of eternity, whispers emerge. Oscillations, ripples, alignments too deliberate to be chance. They resemble the marks of a clock, a metronome written not in gears or pendulums, but in the trembling of space-time itself. The paradox deepens. The universe has an age 13.8 billion years, traced from its beginning, yet the laws that govern it, the quantum fields and constants that bind reality, seem to speak of something older, something timeless. Could there exist a clock older than creation, embedded in the foundations of physics, ticking not in seconds or centuries, but in cycles of existence itself? Humanity measures time with fragile machines of metal and glass, but the cosmos may keep its own time, a rhythm inscribed not on watch faces, but on the structure of galaxies, on the ghostly light of ancient stars. Perhaps time did not begin with the universe. Perhaps the universe itself is only a moment, a single tick of a far older clock whose pendulum swings beyond creation. Since the dawn of civilization, humanity has sought to measure what cannot be touched. Time, the silent current flowing beneath all things. Ancient people first looked skyward, watching the cycles of the sun and the moon, the rising and setting of stars. Each dawn was a reassurance that the world still moved forward. Each lunar cycle, a reminder of continuity. Sundials carved shadows into stone, water clocks stripped away the moments, and hourglasses let sand fall like grains of mortality to early minds. Time was not abstract. It was tethered to motion of stars, of seasons, of bodies aging. Time was the harvest and the flood, the waxing and waning of moons. Without motion, there was no way to measure it. Time and change seemed indistinguishable. Yet in the 20th century, everything shifted. Albert Einstein revealed that time was not simply a sequence of moments, but a dimension woven with space itself, space-time, elastic and malleable. Clocks did not tick at the same rate everywhere. Gravity could stretch time, and velocity could slow it. The universe was not ruled by a single universal metronome, but by relative flows, different for every observer. In 1905 and 1915, relativity reframed time as geometry. It was no longer the background of the plate, was part of the stage. Still, relativity did not end the search. If time was flexible, what then was its foundation? Could there be a deeper rhythm, one immune to relativity's distortions? The next great leap came not from human imagination, but from the universe itself. In 1965, two engineers at Bell Labs, Arno Penzias and Robert Wilson, were tuning a radio antenna when they discovered a faint, persistent noise, a microwave hiss that seemed to come from every direction in the sky. They tried everything to eliminate it, even cleaning bird droppings from the antenna. But the signal persisted, uniform, eternal. Unbeknownst to them, they had stumbled upon the cosmic microwave background, the afterglow of the Big Bang. This light, stretched into microwaves by billions of years of cosmic expansion, was the oldest, signal humanity had ever detected a fossil glow from when the universe was only 380,000 years old, a relic of creation. But what lay hidden in this glow would change cosmology forever. As satellites like COBE, WMAP, and later Planck mapped the background with increasing precision, scientists noticed it was not perfectly uniform. Tiny fluctuations, temperature differences, as small as 1 part in 100,000, were etched across the sky. They were not noise, they were structure. These patterns, these faint ripples, were believed to be the fingerprints of quantum fluctuations, microscopic tremors in the primordial vacuum, stretched to cosmic scales by a moment. A violent expansion known as inflation. Alan Guth, Andre Linde, and others developed this idea in the late 20th century. In the first fraction of a second, the universe ballooned faster than the speed of light, smoothing its structure while amplifying its quantum seeds into galaxies and stars. If true, then these ripples were not just random, they were the ticks of a primordial clock. The expansion itself, driven by hidden fields, carried a rhythm, an oscillation, leaving its imprint on the heavens. Paul Dirac, decades earlier, had glimpsed something equally mysterious. In the 1930s, he proposed the large numbers hypothesis, noting uncanny coincidences between the constants of nature ratios involving the strength of gravity, the age of the universe, and atomic structure. These coincidences seemed precise, to be accidental. Could they reflect a deeper order, a hidden rhythm beneath physics? Dirac speculated that perhaps the constants themselves varied with cosmic time, as though tethered to an unseen metronome. His suggestion was controversial, but it planted a seed. Perhaps the laws of the universe were not timeless after all, but linked to a deeper, older clock. As the 20th century progressed, evidence mounted that something like a cosmic rhythm was indeed real. Astronomers uncovered baryon acoustic oscillations, fossilized sound waves frozen into the distribution of galaxies, echoes from the early universe when matter and radiation vibrated together. These oscillations functioned like a yardstick across billions of light years, another remnant of the primordial ticking. The concept of a primordial clock grew more tangible. If inflation occurred, then the energy fields that drove it may have oscillated, producing distinct patterns in the CMB. Detecting these would be like hearing the heartbeat of the cosmos before it was born. The search expanded to gravitational waves, ripples in spacetime itself. If inflation happened, it should have generated waves that would leave a subtle polarization pattern in the CMB. Instruments like BICEP 2 and future observatories like CMBs 4 and LISA hunt for these faint echoes. Each wave would be a tick from before the universe as we know it, a record of a deeper chronology. Meanwhile, black holes began to complicate the picture. In 1974, Stephen Hawking demonstrated that black holes were not eternal prisons. Quantum effects near their horizons would make them radiate, slowly evaporating over time. This radiation, faint and nearly impossible to detect, implied something radical. Space-time itself had a quantum rhythm. Horizons were not silent, they whispered. Could these whispers, too, be part of the same ancient clock? Step by step, science revealed layers of time older than the familiar. Human clocks were built from pendulums and cesium atoms. Cosmic clocks were etched in light, in ripples, in gravitational tremors, and deeper still, in the strange alignments within the cosmic microwave background, patterns so perplexing that cosmologists gave them unsettling names. One was called the axis of evil, a strange alignment of fluctuations in the CMB, inconsistent with standard models of randomness. Was it coincidence? Or was it another signature of something older, something that preceded creation? The narrative of time began to fracture. On one level, the universe was 13.8 billion years old, its age defined by the expansion from the Big Bang. But beneath that, hidden in ripples and alignments, might lie something timeless, a rhythm older than the universe itself. This discovery phase is not complete, for the evidence is incomplete. But the hints are there, spread across sky maps, galaxy surveys, and equations scribbled on chalkboards. A pulse, a pattern, a whisper of order beneath chaos. The question rises, if there is a clock older than creation, where is it written? In the constants of nature, in the quantum fields beneath spacetime, or in the very act of existence repeating itself, in cycles of universes born and reborn. What began with sundials and stars has brought humanity to the edge of an abyss. Perhaps the true clock does not tick in seconds or years, but in eons of birth and collapse. Perhaps our universe itself is only a moment, one swing of the pendulum in a clock that has always been and will always be. The universe was supposed to have a beginning. The Big Bang was the cleanest, simplest story. Time itself erupted from nothing, an origin point from which everything unfolded. Space expanded, matter cooled, galaxies formed, time's arrow pointed firmly forward. There was no before, because before had no meaning. But then, evidence began to disturb this narrative. The cosmic microwave background, once thought to be nearly perfect, carried strange scars. Subtle alignments, peculiar cold spots, patterns too coherent to be dismissed as chance. These imprints were not easily reconciled with the notion of a simple beginning. They whispered that perhaps the universe bore memories and memories older than itself. The implications were staggering. If the universe carried a rhythm, a sequence of oscillations from before the Big Bang, then the Big Bang was not the beginning, but only a transition. Einstein's theory of relativity, the foundation of modern physics, was clear. Time and space were inseparable. Time was born with the universe, but quantum mechanics painted a different picture. It spoke of fluctuations, probabilities, fields that existed independent of classical beginnings. The two frameworks collided. How could time both begin at creation and leave behind traces of something older? Cosmologists called these traces primordial oscillations. They were not random fluctuations, but patterned as though driven by a clock-like mechanism. Inflationary theory predicted such oscillations. If the universe had inflated exponentially in its infancy, quantum ripples would stretch and freeze, leaving behind the faint pulse of an ancient metronome. But inflation was itself unsettling. It implied that before the observable universe, there was a processor mechanism already in motion. Something had to power inflation. Something had to tick. The Big Bang was no longer the beginning. It was an aftershock of a deeper event. Then came the revelations of black holes. When general relativity first predicted them, they were considered mathematical curiosities, absurd solutions to equations, but evidence mounted collapsed stars could form such singularities. By the mid-20th century, black holes were not only possible, they were everywhere, millions of them scattered across galaxies. Silent anchors of gravity. Stephen Hawking's work added a devastating twist. In 1974, he showed that black holes were not eternal. Quantum fluctuations near the event horizon would create particles radiating faint heat-hawking radiation. Black holes could evaporate. The shock was twofold. First, Hawking radiation meant that space-time itself had a quantum heartbeat. Horizons were not absolute barriers, but dynamic, whispering surfaces. Second, this radiation suggested that information, the fundamental currency of reality, could be destroyed, vanishing into nothing as black holes evaporated. If information could be lost, then the past itself was not safe. Reality's clock could be broken, its memory erased. Physics recoiled at this thought. Hawking's paradox challenged the very bedrock of science. Laws of physics depend on determinism. The present encodes the past. Without this, the universe is incoherent. But the mathematics implied otherwise. Once again, time was not behaving as expected. Other shocks came from quantum entanglement. Einstein had once derided it as spooky action at a distance, an affront to relativity's insistence that no information could travel faster than light. Yet experiment after experiment confirmed it. Entangled particles behaved as if connected by invisible threads. No matter how far apart, Juan Moldacena and Leonard Susskind would later propose the EPR conjecture that entanglement and wormholes were two sides of the same coin. Every entangled pair could be seen as linked by a microscopic Einstein-Rosen bridge, a hidden tunnel in space-time. If true, then the universe was laced with bridges at every scale, invisible connections woven into its fabric. But the implication was far greater. Entanglement was instantaneous. It did not respect the ticking of clocks. It suggested that causality itself might not be absolute. Cosmology, too, was shaken by the discovery of dark energy. In 1998, astronomers measuring distant supernova found that the universe was not just expanding, it was accelerating. Some hidden energy was pushing space-time apart, acting like a cosmological constant. The revelation was profound. Dark energy behaved with perfect steadiness, unchanging across billions of years. It was as though the universe had a hidden metronome, pressing outward at a constant beat, indifferent to matter, galaxies, or time itself. The more physicists measured, the more the paradox grew. The vacuum itself seemed to contain energy, a vast reservoir invisible to all senses, yet dictating the fate of the cosmos. Was this vacuum energy the true clock older than creation? A timeless force embedded in the fabric of reality, indifferent to beginnings or ends. The discoveries compounded into dread. If the universe carried signals from before its birth, if black holes whispered of quantum rhythms beyond time, if entanglement defied causality, if dark energy pulsed eternally, then what did it mean for the notion of creation? The Big Bang was no longer the pristine origin of time. It was a doorway, one frame in a longer reel. The clock had been ticking before the screen lit up. The shock was not confined to equations. It was existential. Humanity had always asked, where did it all begin? The answer had been clear for decades, with the Big Bang. But now, that answer seemed naive. Physicists wrestled with the paradox. If there was a deeper clock, where was it located? Was it quantum? Was it geometric? Was it informational? Some began to suggest that time itself might be emergent, that it arises not from a fundamental ticking, but from entanglement and entropy. In this view, the universe has no baseline clock. What we call time is merely a shadow of deeper laws, patterns that exist without chronology. Others argued that inflation, black hole, evaporation, and entanglement all pointed to a single truth. The universe is governed by processes that extend beyond creation, rhythms embedded in reality itself. The clock is real, but it is not ours to read. The greatest shock of all was philosophical. If the universe is not the beginning, then neither is the present. Time as we experience it forward measurably is only a layer. Beneath it, something else persists, something unchanging. A timeless rhythm, older than stars, older than light. It was as if science had torn away the veil of creation, only to find another veil behind it. The Big Bang had not ended the mystery, it had deepened it. The discovery that there may be a clock older than creation was not a triumph, but a wound of fracture in the story of existence, one that refuses to close. The shock was undeniable. If the universe bore scars from a rhythm older than itself, science could not turn away. It had to look closer, with sharper tools, with deeper patience. Discovery became a matter of precision, of listening for whispers. Across cosmic silence, the first instruments were crude. In 1965, Arno Penzias and Robert Wilson stumbled upon the cosmic microwave background, the afterglow of creation itself. Their antenna, built for satellite communication, caught a faint hiss that would not go away. At first, they blamed pigeons nesting inside the device. But after cleaning, after recalibration, the signal remained, a uniform glow across the sky. The cooled radiation of the Big Bang. This discovery transformed cosmology. For the first time, scientists had a fossil light, a canvas imprinted with the earliest moments of the universe. But it was only the beginning. The hiss was not perfectly smooth. With finer instrument scope in 1989, WMAP in 2001, and Planck in 2009, cosmologists uncovered delicate fluctuations, minute variations in temperature across the cosmic sky. These ripples were not noise. They were structure. Each fluctuation told a story. Quantum ripples stretched to cosmic scales by inflation. The universe's earliest moments preserved like fingerprints on glass. Some patterns resembled oscillations, faint beats from a primordial process. They were not random scatterings, but structured, like echoes of a clock striking long before the universe cooled into transparency. Scientists called them baryon-acoustic oscillations. In the first 380,000 years after the Big Bang, the universe was a plasma hot, dense, opaque. Sound waves rippled through this medium, pressure fronts of matter and light moving in tandem. When the universe cooled and photons escaped, these ripples froze, preserved in the clustering of galaxies billions of years later. Like fossils in stone, they recorded a beat, the universe's first sound, the resonance of a clock embedded in spacetime itself. But the cosmic microwave background offered more than sound. It carried alignments, peculiar symmetries, even anomalies. The so-called axis of evil, a strange large-scale alignment of fluctuations, hinted at something more profound. Was this the trace of pre-inflationary structure, an imprint of conditions older than the universe? Or was it merely statistical coincidence? The debate rages still, unresolved, the possibility of a deeper rhythm never fully banished. To probe further, physicists turned to the smallest scales. Quantum theory predicted fluctuations in the vacuum itself, seething particles and antiparticles emerging and vanishing in fractions of Planck time. During inflation, these quantum fluctuations would have been stretched, magnified to cosmic proportions. If inflation occurred, then quantum jitter became the scaffolding of galaxies. The tick of a subatomic clock, scaled upward, became the rhythm of creation. But could such primordial oscillations be measured directly? The answer lay in gravitational waves. In the mid-20th century, Einstein's general relativity predicted that massive objects in motion would ripple spacetime itself. But detecting these waves required impossible sensitivity distortions, smaller than a proton's width. For decades, the quest seemed hopeless. Then, in 2015, LIGO detected the merger of two black holes over 1 billion light-years away. Space-time had trembled, and Earth had listened. This breakthrough opened new doors. If black hole mergers could be heard, perhaps the universe's birth cries could be too. Primordial gravitational waves, if they existed, would be the purest evidence of a clock predating creation. They would carry the frequency of inflation itself, a vibration older than light, woven into the first moments of time. The search continues. Advanced LIGO, Virgo, Kagra, and future missions like LISA aim to listen across the spectrum of spacetime, hunting for echoes from before the Big Bang. Meanwhile, pulsar timing arrays cosmic clocks in their own right measure. The arrival of radio pulsars from spinning neutron stars. Variations in timing might betray gravitational waves stretching spacetime on galactic scales. Already, hints of such a background have begun to appear. The first steps toward hearing the universe's deepest rhythms. Yet even as instruments probed the cosmos, theorists ventured into more radical domains. Roger Penrose proposed conformal, cyclic cosmology, that the universe did not begin, but cycles endlessly. In his vision, the remote future of one universe becomes the Big Bang of the next. The cosmic microwave background, he argued, should carry imprints of events from before our Big Bang, such as the final evaporation of black holes in a previous eon. He pointed to circles in the CMB as evidence, though the interpretation remains contested. If Penrose is right, then the clock older than creation is not metaphor, but reality. Time itself is cyclical, each universe a tick in an infinite pendulum. Others explored loop quantum gravity, which suggested space-time is not smooth but discrete. At the Planck scale, time itself may advance in quanta, like frames of film. If so, the deepest clock is not continuous, but granular, sequence of indivisible ticks that existed before the Big Bang and continue beyond it. String theory offered yet another vision. Extra dimensions culled beyond our perception might host oscillations, resonances invisible to ordinary senses. These vibrations could act as clocks older than creation, their beats setting the tempo of inflation, shaping the constants of nature, orchestrating the evolution of universes. But perhaps the most haunting clue came from entropy. Entropy, the measure of disorder, gives time its arrow. Our universe began in a state of low entropy, improbably ordered, and has been increasing ever since. But why? If time began at the Big Bang, why did entropy not begin high? Some physicists speculate that entropy itself is the deeper clock, ticking beneath universes, persisting across creation and destruction. The deeper the investigation went, the stranger the questions became. Was the clock physically literal oscillation of fields, particles, or waves? Or was it informational, encoded in the structure of reality? Was time itself emergent, born from entanglement and thermodynamics, with no fundamental tick at all? The search for answers drove experiments into the depths of Earth. Neutrino detectors, buried under mountains and ice, watched for ghostly particles streaming from the sun and distant supernova. These elusive messengers carried information about processes invisible to light. Some theories suggest neutrinos themselves may encode rhythms from the earliest universe. Their oscillations, a trace of hidden clocks. Supercomputers, too, became essential tools. By simulating inflation, cosmic structure, and quantum fields, scientists tested hypotheses of primordial oscillations, patterns in galaxy clustering, voids, and dark matter halos were compared to models. Each match strengthened the possibility of a clock-like process before the Big Bang. Each mismatch sharpened the mystery. Even in laboratories, analogues of cosmic processes were pursued. Bose-Einstein condensates, supercooled atoms behaving as a single quantum entity, were used to simulate horizons, mimicking the physics of black holes. In these cold experiments, hints of Hawking-like radiation emerged, tiny whispers of clocks embedded in quantum fields, imitated in miniature. Through every channel, one truth grew clear. The investigation was not uncovering a single mechanism, but a convergence, from the cosmic microwave background to gravitational waves, from entropy to quantum fluctuations. Every clue pointed to the same possibility, that the Big Bang was not a beginning, but a transformation. The deeper scientists looked, the more the notion of a clock older than creation seemed unavoidable. It might not be a clock as humans imagine it, with gears and hands. It might be woven into the fabric of mathematics, in constants that do not change, in symmetries that persist. It might be a rhythm not of time, but of reality itself, beyond beginnings, beyond endings, in the silence of data, in the faint whispers of radiation and ripples. The universe seemed to murmur, "I am older than I appear." And so the investigation continued, not as a search for origin, but as a recognition that creation itself was only part of a larger rhythm, eternal ticking, older than stars, older than space, older than time. The deeper scientists gazed, the less reassuring the universe became. What began as faint, anomalous, tiny fluctuations in the microwave background, suspicious alignments, improbable symmetries, grew into questions that threatened the very foundations of physics. For centuries, time had been treated as a steady flow, a measure of change, the rhythm against which the universe played its music. But now, the evidence suggested something more disturbing. Time might not be fundamental. It might be the shadow of a deeper rhythm, a clock ticking beneath the stage of creation itself. The first cracks widened with entanglement. Quantum mechanics had long whispered that causality was not absolute. In 1935, Einstein, Podolsky, and Rosen protested that particles could not instantaneously affect each other across distance. Such spooky action was impossible. Yet experiment after experiment proved them wrong. Entangled particles behaved as if connected by invisible bridges, correlations appearing instantly no matter how far they were separated. If entanglement could bypass the ordinary flow of time, then what was the true measure of sequence? Some physicists began to suspect that entanglement itself was the deeper, clock-binding rhythm across space. Older than any Big Bang. Inflation deepened the mystery further. According to the theory, in the first fractions of a second after the Big Bang, the universe expanded exponentially, faster than light itself. This inflation smoothed the cosmos, explaining its large-scale uniformity. But inflation was not a gentle process, oscillated. Quantum fields driving expansion would have vibrated, leaving imprints in the distribution of matter. When cosmologists analyzed Planck's maps of the microwave background, they found hints of such oscillations. They were subtle, but persistent. Wiggles in the power spectrum, periodicities where none should be. Some interpreted them as the beat of a primordial clock, the pendulum swing of fields that existed before ordinary time began. Roger Penrose escalated the tension further. His conformal cyclic cosmology suggested that our universe was not unique, nor was it the beginning. Instead, it was one phase in an endless succession of eons, each universe fading into the next. He claimed to see circles in the CMB, imprints of black holes evaporating in a previous cosmos. If true, then the Big Bang was not a beginning but a transition. The clock was not reset with each universe. It continued, unbroken, through cycles of creation and death. This was not the only troubling sign. Entropy, the arrow of time, refused to align neatly with the universe's youth. By every thermodynamic principle, the cosmos should have begun in chaos, a high entropy state. Yet the opposite was true. The early universe was improbably smooth, improbably ordered. Why? Some physicists propose that entropy itself was the deeper rhythm, the universal metronome. It did not begin with the Big Bang. It had been ticking. Long before, its increase merely continuing through different phases of reality. If entropy predated creation, then time's arrow was older than spacetime. Dark energy complicated everything further. In the late 1990s, astronomers discovered that the expansion of the universe was accelerating, driven by an invisible energy-saturating space. Unlike ordinary energy, dark energy did not dilute as the universe expanded. It remained steady, constanter, perfect clock-like force. For billions of years, it has pushed the cosmos outward with unchanging persistence, as if it follows a rhythm older than galaxies, older than stars. Could dark energy itself be the hand of the primordial clock, ticking steadily as universes are, born and destroyed? Some think so. Its constancy defies ordinary physics. It seems timeless, indifferent to cosmic history, a force that belongs to eternity rather than time. Other signs emerged from the structure of galaxies. Supercomputer simulations of cosmic evolution revealed filaments and voids stretched across billions of light-years. The cosmic web resembled a vast lattice, as though shaped by a hidden geometry. Some wondered, was this lattice the frozen imprint of oscillations that began before the Big Bang? Could the shape of the universe itself be the fossil of a deeper metronome? Black holes brought the greatest escalation of all. At their centers, time ceases. Horizons form barriers beyond which nothing escapes. Yet Hawking's equations revealed that even these silent tombs glow faintly, radiating over eons until they evaporate. This evaporation is not random, it follows precise laws, bound to entropy, tied to information. Some physicists argue that black holes may be tied to the primordial clock. They act as timekeepers of a hidden order, ticking invisibly as they shrank. But the implications were terrifying. If wormholes or quantum entanglements are linked to black holes, as the ER equals EPR conjecture proposes, then every entangled particle in the universe may be a micro-wormhole, a hidden bridge tied to a cosmic clock older than creation. In this view, time itself emerges not from smooth flow, but from the geometry of entanglement. The escalation was not only scientific, but existential. If time predates the universe, then our cosmos is not the foundation of reality. It is only one phase in a deeper, timeless process. Our notion of beginnings collapses. The story of existence stretches into infinity, and so the dread grows. If the clock is eternal, then universes are disposable. Creation is not special. We are one fleeting tick in an endless sequence, no more privileged than any other, yet hope also emerges from the same realization. For if the clock continues beyond creation, then nothing is ever truly lost. The universe may die, but the rhythm persists. Stars may fade, galaxies may unravel, but the clock that predates creation will still tick. In that persistence lies continuity, perhaps even memory. The escalation is undeniable. From entanglement to inflation, from entropy to dark energy, from black holes to the cosmic web, every clue points toward the same conclusion. The Big Bang was not the beginning. It was an event within a deeper story, a chapter in an eternal rhythm. The mystery deepens not because the evidence is scarce, but because it is abundant whispers from every scale, from the smallest quantum to the largest cosmic web, converging on the same unsettling truth. The clock older than creation is no longer speculation. It is the shadow behind the laws of physics, the rhythm beneath existence, and as science listens more closely, the ticking grows louder. The universe, to human intuition, begins with a line, a first moment, a singularity of fire, a beginning beyond which no questions should reach. For centuries, cosmology clung to the comfort of boundaries, the assumption that there was once nothing, and then, suddenly, something, a clean slate, a birth event. But science is rarely merciful with simplicity. Beneath the glow of the Big Bang's afterlight, whispers appeared, traces that did not belong to a universe with a single, finite start. The shock began not with grand explosions, but with faint irregularities. In 1965, Arno Penzias and Robert Wilson, tuning a microwave receiver at Bell Labs, stumbled upon the cosmic microwave background, the fossil radiation of creation itself. It was expected to be smooth, a perfect backdrop of light, the cooling embers of the universe's fiery birth. Yet later, satellite scope, WMAP, Planck revealed something else. Delicate fluctuations, tiny variations in temperature, only millionths of a degree apart. These ripples seemed to be imprints of quantum fluctuations, amplified and frozen during inflation. They were not chaos. They carried patterns, rhythms, almost as though a clock had been ticking before creation itself. Its marks etched into the fabric of the newborn cosmos. The deeper scientists looked, the more troubling the story became. The discovery of the so-called axis of evil, an alignment of temperature, fluctuations in the cosmic microwave background across vast stretches of the sky should not exist if the universe's birth were entirely random. Instead, it suggested something coherent, structured, predating the expansion. A scar, a rhythm, a metronome hidden beneath the apparent noise. Two physicists raised on Einstein's relativity. This was a profound violation of expectation. Einstein's equations framed spacetime as a fabric that begins at the Big Bang with no before. Time, space, energy all emerge together in one indivisible moment. To ask what came earlier is meaningless, like asking what lies north of the North Pole. Yet the data whispered of influences not bound by this restriction. If the cosmic clock ticked before the Big Bang, then time itself did not begin with creation. The emotional weight of this realization was immense. For decades, the Big Bang was more than theory. It was the story of ultimate origins. It replaced myths of fire and gods with physics and expansion. It offered a beginning we could measure, roughly 13.8 billion years ago. But now, physicists were confronted with evidence that the story might not be complete. Worse, that the opening page might not be the true beginning at all. inflation theory added fuel to the fire. Alan Guth, Andrei Lind, and Alexei Starobinsky proposed that in the first fraction of a second after the Big Bang, the universe underwent exponential expansion, stretching quantum fluctuations into the seeds of galaxies. This explained why the cosmos looks so uniform across unimaginable distances. Yet inflation implied something disturbing. The process was not a simple event. It behaved like an engine, powered by fields that could oscillate, repeat, or even continue eternally. The faint oscillatory signatures detected in the cosmic microwave background suggested a hidden pendulum, a rhythm guiding creation itself. Inflation, instead of solving the mystery of beginnings, had revealed a clock that might predate them. The shock grew deeper still with the problem of entropy. The second law of thermodynamics declares that entropy disorder always increases. But if the universe truly began with the Big Bang, why did it begin in such a state of extraordinarily low entropy, so finely tuned as to allow order, structure, and life? Why does the arrow of time point forward, not back? These questions suggested that the Big Bang was not the reset it appeared to be. Something else was preparing the stage, maintaining conditions, perhaps ticking like a clock. Before creation's fiery expansion, then came the black holes. These enigmatic objects, predicted by Einstein's equations and confirmed by observation, embodied paradoxes of time. At their hearts lies the singularity, a point where relativity collapses and time ceases to make sense. Stephen Hawking, through his work on black hole thermodynamics, introduced yet another shock. Black holes are not eternal prisons. Quantum effects cause them to radiate energy. Hawking, radiation slowly evaporating over trillions of years. This linked gravity, quantum physics, and thermodynamics in one unsettling framework. But the implications cut deeper. If black holes radiate, then time itself, within their event horizons, may be governed not by relativity alone, but by some deeper clock hidden beneath. The conceptual earthquake came when some cosmologists suggested that the universe itself might be governed by the same rules. The Big Bang, instead of being the ultimate beginning, might be the rebound of a black hole-like state. Time, instead of starting there, might only appear to. The true clock might be older, pulsing beneath even singularities. Einstein, for all his genius, never accepted such implications lightly. To him, nature should forbid singularities or beginnings without cause. Yet his equations, relentless in their logic, predicted them. Hawking and Roger Penrose proved in their singularity theorems that under general relativity, singularities were inevitable. Still, the equations also hinted that our laws of physics are incomplete at those extremes. If a clock older than creation exists, it hides in the gaps where relativity fails and quantum theory has not yet taken hold. Philosophically, the shock was devastating. Humanity measures time with fragile instruments, pendulums, quartz crystals, atomic oscillations. Each clock assumes a beginning, a 0 point. But if the universe itself is etched with rhythms older than its own birth, then our notion of time is provincial. Our clocks measure moments within a larger order, blind to the pendulum beneath creation itself. This revelation struck at the heart of cosmology's comfort. For decades, the narrative of a finite beginning had aligned with human intuition, even with ancient myths of creation. Now, science was proposing something stranger, that time may not have begun with us, that the universe may carry memory, rhythm, and order from epochs predating its own birth. The shock was not merely academic. It carried with it a profound unease. If a clock older than creation ticks beneath reality, what does it measure? Does it count cycles of universes, endless births and deaths? Does it mark a deeper law, unknown and inaccessible, governing not only matter and energy but existence itself? Or does it simply reveal that time, as we know it, is not fundamental but emergent, an illusion arising from something timeless? The scientific community wrestled with these possibilities. To some, the data were anomalies, noise, or coincidence. To others, they were whispers of truths too vast for current theory. But to all, the shock remained. The universe may not be young, nor finite in its chronology. It may be one heartbeat in an eternal clock, older than creation, older than time itself. And so, the story pressed forward. What had begun as subtle patterns in background radiation had grown into a crisis of comprehension. Scientists stood before a paradox. Either their measurements were flawed, or the cosmos itself carried a rhythm from before the dawn of everything. In either case, the consequences were enormous. The shock was clear. The universe may have been born, but the clock it follows might be eternal. The shock had settled, but the mystery deepened. If the universe carried rhythms older than its birth, then science had to listen more carefully. The cosmos, once thought to be a silent expanse punctuated by light, revealed itself as an archive. A layered manuscript in which every ripple and fluctuation was a trace of something earlier. Humanity's task became not merely to look outward, but to tune its instruments to the faintest of echoes, the most delicate of signature signs of a clock hidden beneath creation. The first great tool in this quest was the satellite. In 1989, the Cosmic Background Explorer COBE was launched. Its mission was to measure the afterglow of the Big Bang with unprecedented accuracy. What it found was extraordinary. Instead of a perfect, featureless glow, COBE revealed tiny temperature variations across the sky anisotropies in the cosmic microwave background. These ripples were fossils of sound waves, baryon acoustic oscillations that had moved through the infant universe like vibrations in a drum. Each oscillation froze. As the cosmos cooled, preserved forever in the distribution of galaxies. They were not noise. They were ticks beats of a primordial clock written into the sky itself. A decade later, the Wilkinson Microwave Anisotropy Probe, WMA, peer-refined. These measurements, the ripples became sharper, the patterns clearer. Then came Planck in 2009. Mapping the CMB with exquisite resolution, Planck's data suggested not only quantum fluctuations stretched by inflation, but possible oscillatory features, subtle, repeating modulations that looked like a pendulum's trace across the cosmos. To some, this was confirmation. The universe's birth carried memory of a deeper rhythm, one that could not have emerged from chaos alone. Beyond the microwave sky, the investigation reached into structure itself. Galaxies are not scattered randomly. They gather in filaments and walls, leaving vast cosmic voids between. This architecture, revealed in surveys like the Sloan Digital Sky Survey, echoed the same oscillations detected in the CMB. It was as though the entire cosmic web was shaped by a primordial metronome. Each cluster, each filament, each vast emptiness was frozen music, a harmonic echo of the first vibrations. But if these were ticks of a cosmic clock, what was the mechanism? Inflation theory, with its rapid expansion, predicted just such frozen imprints. Yet inflation itself raised questions. What field drove it? What oscillated? Could the inflaton, unknown quantum field have acted as the pendulum of creation? Some models suggested periodic features in the inflaton potential, generating repeating signatures across the CMB. If so, the universe was not a spontaneous eruption, but the unfolding of a deeper cycle. The investigation widened further. Physicists turned to gravitational waves, ripples in space-time itself. If the primordial clock existed, its beats might not only be frozen in light, but also in the trembling fabric of space-time. Detectors like LIGO and Virgo, designed to capture the cataclysms of merging black holes and neutron stars, hinted at a greater possibility: the detection of primordial gravitational waves, echoes from the inflationary era. Such a signal would be a direct fingerprint of oscillations older than the Big Bang's visible light. Though elusive, the search continued. Pulsar timing arrays, using the precision of rapidly spinning neutron stars, listened for background hums. In spacetime, space missions, like the proposed laser interferometer space, Antenna promised even greater sensitivity, hunting the low-frequency waves that might carry imprints of the universe's earliest beats. If detected, these would be fossils not of sound, but of time itself. Meanwhile, another frontier emerged: quantum cosmology. Physicists sought to merge general relativity and quantum mechanics to peer into the Planck era, the unimaginably brief instant before conventional time begins. Within this realm, concepts like conformal cyclic cosmology, proposed by Roger Penrose, gained traction. Penrose suggested that the universe is not unique, but cyclic, each Big Bang merely the handover between eons. In this vision, the clock is not metaphorical. Each universe is a tick, and the alignments in the CMB may be scars left by black holes evaporating in a previous cosmos. Planck data even suggested faint concentric circles controversial, but tantalizing that might be evidence of such cycles. At the smallest scales, time itself became granular. Loop quantum gravity, a framework seeking to quantize spacetime, suggested that the continuum of time may dissolve into discrete steps, the way matter dissolves into atoms. If true, the clock older than creation is not hidden but fundamental, the lattice of reality itself. Each Planck interval, y-43 seconds, becomes the universe's true heartbeat. Within such brevity, the Big Bang is not a singularity but a transition, one tick among countless before and after. The search extended even into the nature of constants. Paul Dirac, decades earlier, had noticed curious relationships between large dimensionless numbers in physics: the strength of gravity, the age of the universe, the charge of the electron. He wondered if these coincidences were not chance, but signs of a deeper rhythm, a hidden law tying the universe's constants to a clock beyond creation. Modern physics has not resolved his hypothesis, but the suspicion lingers. Perhaps the constants themselves are ticks of a deeper pendulum, unfolding across aeons. To probe these mysteries, science demanded new tools: neutrino observatories, buried deep beneath mountains and ice, measured particles ghosting through matter from the earliest nuclear reactions. These neutrinos, largely unaffected by intervening matter, carried information from epochs long hidden to light. Super Kamiokande in Japan, IceCube in Antarctica, and the future Hyper Kamiokande sought not only to understand stars and supernova, but to capture whispers of rhythms older than galaxies. The Casimir effect, a subtle force observed between metal plates in a vacuum, revealed that even empty space teams with energy 0-point fluctuations. If the vacuum itself pulses, then perhaps the primordial clock is woven into this seething quantum foam, oscillating beneath reality in ways we barely perceive. Laboratory experiments with Bose-Einstein condensates even sought to simulate horizons, probing Hawking-like radiation to glimpse how clocks might emerge from quantum fields. And yet, with every deeper probe, the questions multiplied. If the universe carries rhythms from before its beginning, what does that mean for causality, for the arrow of time, for the very meaning of before? If the clock is older than creation, does creation ever truly begin? Or are beginnings themselves illusions, chapters in an eternal cycle? The deeper investigation revealed more than data. It revealed philosophy. Humanity, fragile and brief, listens for ticks not of seconds but of cosmic eons, with satellites orbiting Earth, with detectors buried in ice, with theories extending beyond imagination. It strains to hear a rhythm that may never have had a first note. The search is both scientific and existential, for to find the clock older than creation is not merely to understand the cosmos, it is to confront the possibility that beginnings and endings are illusions, and that existence itself may be nothing more and nothing less than the swing of a timeless pendulum. The investigation had begun with faint ripples in ancient light. It now spanned telescopes, detectors, colliders, and theories stretching from the quantum to the infinite. Each new piece of evidence whispered the same unsettling possibility. The universe carries memory, a rhythm that does not belong to creation alone, but to something deeper, older, more enduring. And so the deeper investigation left humanity not with answers, but with a haunting realization. Perhaps the universe itself is not the clock. Perhaps it is only one tick, one luminous beat, in a rhythm far older than the stars. The evidence had grown into a quiet chorus, faint oscillations in ancient light, the fossil of sound preserved in the cosmic web, gravitational murmurs threading the dark, yet none of it declared outright what the clock might be. To cross that threshold required theory bridges of mathematics cast toward horizons that observation could not yet reach. In this realm, physics walks a narrow path, one foot upon data, the other upon imagination disciplined by law. The first bridge returns to inflation. If a clock older than creation left its trace, inflation is where it most likely imprinted it. In many models, the field that powered the universe's exponential expansion, the inflaton does not drift smoothly. It can oscillate, ring like a plucked string as it rolls across its potential. Such periodicities would lace the primordial power spectrum with ripples, small, repeating modulations in the temperature pattern of the cosmic microwave background and in the distribution of galaxies. These primordial oscillations are not proof of a pre-cosmic metronome, but they are its most natural signature inside standard cosmology, a pendulum hidden in the field that set the stage for everything that followed. A bolder bridge is drawn by conformal cyclic cosmology. In Roger Penrose's vision, the remote future of a universe after black holes have evaporated, after matter has thinned into radiation, can be mathematically rescued to resemble a new Big Bang. One eon hands its almost empty, cooled geometry to the next, with the conformal structure of spacetime acting as the hinge. The clock, in this picture, does not start, it turns. What looks like origin is merely inheritance. Penrose has pointed to subtle circles in the microwave background, as possible scars from the deaths of black holes in a previous eon, rings where information-rich eruptions might have left their ghosts in our sky. The claim is controversial, the evidence contested, yet the idea is precise. A clock measured not in seconds, but in eons. It's ticked the passing of a universe. Other bridges recast time itself. In loop quantum gravity, spacetime is quantized. Area and volume come in discrete units, knitted by a network of finite links called spin networks. Evolving in quantum steps, the geometry advances in jumps at the Planck scale. Time, then, is not a river but a sequence frames in a cosmic film. The oldest clock may be the lattice of existence itself, its minimal tick the Planck time. 10:43:10:43 10:43 seconds. In this telling, the Big Bang is not a singular wall but a bounce, a transition between quanta of geometry, before and after our bows allowed, separated by a finite, fundamental beat. String theory offers a different cadence. Here, the universe's constituents are vibrating strings and higher dimensional brains. Extra compact dimensions hum with microscopic modes. Oscillations in those hidden dimensions could modulate physics in our visible world, leaving periodic fingerprints during inflation or in the values of couplings that shaped the early plasma. Some models, axion monodromy, clockwork mechanisms explicitly build oscillatory features into the inflatance dynamics by invoking light axion-like fields with long periods. If such a field exists, its rolling could act as the hand of a primordial clock, its period inscribed on the sky in gentle, repeating waves. Beyond these constructions lies the austere possibility of eternal inflation. In many potentials, inflation never fully ends. It stops locally, birthing bubble universes while the inflating background continues elsewhere. The multiverse becomes a foam, each bubble its own cosmos, each with a history, chemistry, and perhaps different constants. If so, the older clock might not reside in time at all, but in the statistics of this ensemble, a measure that orders births and deaths of universes in an atemporal way. The rhythm is then not the beat of a field, but the branching of spawning, never finishing. A darker speculation regards vacuum stability. The Higgs field defines the masses of elementary particles. Its measured value suggests our vacuum might be metastable perched on a plateau that could, through quantum tunneling, drop to a lower energy state. In that catastrophic transition, a bubble of true vacuum would expand at light speed, rewriting the laws of physics as it passed. If the early universe navigated such landscapes, tunneling and rolling, the sequence of transitions would form a hidden chronologia, chemical clock of fields, each phase bequeathing its memory to the next. In this chemistry of vacua, before creation is simply before this vacuum. At the boundary of gravity and quantum theory, time begins to slip its classical chains. The Wheeler-DeWitt equation, a central equation in canonical quantum gravity, contains no explicit time variable. It is famously written as h psi equals 0, h psi equals 0, h psi equals 0, a timeless constraint on the universe's wave function. If the fundamental equation of the cosmos has no time, then how does time appear? One answer is that time is emergent from entanglement and coarse graining. In the thermal time hypothesis Consrovelli, the flow of time arises from the state of a system and the algebra of its observables. Temperature and entropy define an intrinsic clock. In this view, the oldest clock is not a field that oscillates, but the relational structure of information itself, the way correlations among parts give rise to a directed flow. The Big Bang then marks not the birth of time, but the onset of a new informational regime. Holography sharpens this intuition. The holographic principle, made concrete in a DS-CFT duality, says that a gravitational universe can be encoded on a lower dimensional boundary theory without gravity. In such dualities, time in the bulk can map to renormalization flows or entanglement patterns on the boundary. The page curve and the island formula recent breakthroughs in black hole information show that entanglement wedge reconstruction governs what information is retrievable and when. If time's arrow is tied to how information is shared and recoverable, then the primordial clock may be the growth and rearrangement of entanglement. The Big Bang would correspond to a particular entanglement geometry igniting, not the appearance of a fundamental tick. Other speculative frameworks step differently. Causal set theory proposes that spacetime is a discrete, partially ordered set of events. The order relation itself is the clock. Reality accretes elements one by one, asynchronous. Becoming. The universe's oldest rhythm is simply the growth of this set. An ever-deepening partial order from which continuum. Spacetime emerges as an approximation. There are also varying constant ideas, echoing Dirac's large number intuition, perhaps. The fine structure constant, or the strength of gravity, changes over cosmic epochs in a patterned way. Data so far is largely consistent with constancy, but the possibility remains that subtle drifts trace an underlying cycle, an ancient pendulum, leisurely modulating the very rules. Even within orthodox cosmology, baryon acoustic oscillations and the matter-power spectrum admit oscillatory features beyond the simplest inflationary expectation. If future surveys Euclid, the Roman Space Telescope, the Vera Rubin Observatory were to find statistically significant, scale-dependent wiggles synchronized across probes, they would strengthen the case for a primordial metronome. Such wiggles might be the residue of multiple fields isocurvature, modes interfering like instruments in an unseen orchestra. Speculation can overrun evidence. Theory must return repeatedly to the discipline of test. Fortunately, many of these visions offer concrete footprints. Primordial gravitational waves imprint a distinctive B-mode polarization in the microwave background. A detection with a specific spectral tilt or superimposed fine structure would favor oscillatory, inflated dynamics or hidden sectors. A non-trivial running of the spectral index, periodic in wave number, would hint at an underlying beat, a future census of black hole evaporation, signatures improbable, though direct observation could indirectly favor cyclic scenarios. Pulsar timing arrays, by mapping a broadband gravitational hum, may yet reveal features incompatible with simple astrophysical backgrounds. And if none of these arrive, if the sky refuses the wiggle, if gravitational waves remain featureless, then the older clock may live where experiments cannot yet trespass, in the logic of quantum gravity, in the algebra of observables, in the way entanglement begets duration. The absence of a visible pendulum would not erase the rhythm. It would press the search inward, to the structures from which time itself is distilled. Beneath every speculation, a common refrain persists. The universe could be one act in a longer play, a single expansion among many, a single vacuum among a landscape, a single arrangement of entanglement among innumerable possible webs. The clock, older than creation, need not be a device, or even a periodic function. It can be the persistence of law, the recurrence of transition, the growth of order and disorder through cycles that never quite repeat, by the standards of human clocks, pendulums, quartz, cesium. The cosmos keeps impossible time. It ticks, in eons and phase transitions, in bounces of geometry and rollings of fields, in the patient accretion of a causal set and the sudden flare of a vacuum decay. Theories and speculations do not merely guess at the mechanism. They teach a humility that time may be less a parameter we measure, and more a pattern we inherit. If the clock predates creation, its face is not numbered, its hands not visible. It is felt in alignments across the sky, in the whisper of waves, through space, in the consistency of constants that might themselves be part of a longer breath. The task of theory is to give that breath a name, a model, a place to meet observation. The task of observation is to answer, gently but firmly, yes or no. Between them, the rhythm waits, as patient as law. The search for the clock older than creation is not only a question of theory. It is an experiment of patience, of engineering, of instruments built to measure whispers almost erased by the age of the universe. Human beings, bound to a planet and a fleeting lifespan, have learned to construct tools that extend perception into the oldest shadows. Each device becomes a kind of ear pressed against the silence, listening for a tick that may have sounded. Before time began, the story begins with the cosmic microwave background, the faint afterglow of the Big Bang. In 1989, the COBE satellite first mapped its unevenness. Later, WMAP sharpened the detail. And finally, the Planck Observatory drew a map so precise that it became a monument to precision cosmology. Within these maps, scientists hunt for more than just random noise. They search for periodic ripples, subtle wiggles in the spectrum that would betray an ancient oscillation. Planck's data has placed powerful constraints, yet hints remain features at certain scales that resist smooth explanations. These features are the possible fingerprints of a primordial metronome, an echo of a ticking that predates stars. Next comes the promise of CMBs 4, the next generation of microwave background observatories, spread across Antarctica and the high deserts of Chile. Thousands of detectors will stare at the sky, cooled nearly to absolute zero, searching for patterns of polarization that no astrophysical source can mimic. If a background of primordial gravitational waves exists, seeded during inflation C, MBS4 is designed to detect them. The exact spectrum of these waves could confirm or deny models where oscillating fields marked time before creation. A detection would be more than a triumph of technology. It would be the first audible tick of the oldest clock. Gravitational waves themselves have already become a new astronomy. LIGO and Virgo, with arms kilometers long, have felt spacetime tremble as black holes and neutron stars merged. Yet these are loud, recent events. For the older clock, scientists look deeper, to continuous and stochastic backgrounds. Planned instruments such as LISA, a space-based gravitational wave detector with million-kilometer arms, will listen for much longer. Wavelengths. LISA may detect a primordial fossilized oscillations from inflation stretched across the cosmos. Similarly, pulsar timing arrays, which use millisecond pulsars as galactic clocks, already hint at a low-frequency background. If this background carries features inconsistent with astrophysical populations, it could be the resonance of a universe vibrating before galaxies existed. Light, too, carries memory. The Euclid mission and the Nancy Grace Roman Space Telescope are designed to map billions of galaxies across cosmic time. By tracing how galaxies cluster, they reveal the baryon acoustic oscillations, frozen ripples of sound from the primordial plasma. If superimposed modulations, small, periodic deviations, appear, they may signal an older rhythm inscribed during inflation. The Vera C. Rubin Observatory, with its legacy survey of space and time, will add to this tapestry, capturing the sky's flickers over 10 years. Together, these surveys act like the dial of a cosmic seismograph, sensitive to beats inaudible without statistics written in billions of points. On Earth, the search continues in quieter chambers. Neutrino observatories, such as Cameo-Condi in Japan and IceCube in Antarctica, wait for ghost particles streaming through the planet. These neutrinos carry signatures of nuclear fire and perhaps of exotic processes in the early universe. Future detectors like Cameo-Condi will be sensitive enough to detect neutrinos from the first generations of stars, and possibly from even stranger sources. If patterns of arrival reveal oscillations or unexpected correlations, they could hint at dynamics set by a primordial metronome. Particle physics pushes in parallel. At CERN, the Large Hadron Collider probes the stability of the Higgs field. The Higgs, with its peculiar mass, may decide whether our vacuum is stable or temporary. By measuring its couplings and interactions with greater accuracy, physicists test whether we live in a metastable state poised on the edge of decay. This has direct implications for the clock older than creation. A metastable vacuum may have been inherited from a previous epoch, a frozen moment in a longer chronology. Proposed future colliders, the Future Circular Collider, the International Linear Collider, promise sharper measurements, searching for faint drifts that could betray deeper rhythms in the field itself. Laboratory analogues explore the frontier between experiment and thought. Using ultra-cold atoms, lasers, and Bose-Einstein condensates, researchers have constructed analog black holes, horizons where sound waves behave like trapped light. In these systems, faint radiation resembling Hawking radiation has been observed. Such experiments are crude compared to the cosmos, but they test whether quantum fluctuations can generate time-like rhythms even in controlled environments. Each detection builds confidence that the same mechanisms could operate at scales far older and larger. The vacuum itself becomes a laboratory. The Casimir effect, measured when two plates are brought microscopically close, proves that quantum fields seethe even in emptiness. Precision tests push this further, measuring how fluctuations shift with geometry and boundary conditions. If the vacuum contains structured oscillations, they may reveal themselves here, at scales accessible to human hands. In this way, a laboratory tabletop becomes a window small, but meaningful into the possibility of a ticking that does not depend on stars. The computational realm adds another dimension. Supercomputers simulate universes seeded with oscillating fields, tracking how galaxies, voids, and filaments would emerge under different primordial rhythms. These simulations generate predictions for surveys like Euclid and Rubin, maps of expected alignments, correlations, and anomalies. By comparing simulation to observation, scientists narrow the space of possible clocks. Already, certain oscillatory inflation models have been dismissed. Others remain viable. The process resembles tuning an instrument by ear. Discard the notes that do not harmonize with the sky. Keep those that might. Even the domain of quantum information contributes. Experiments with entangled photons stretch across continents through quantum networks, testing the speed and fidelity of correlations. Though not directly probing the early universe, these experiments explore how time itself may emerge from entanglement. If the arrow of time is tied to the growth of correlations, then quantum networks become small rehearsals of the cosmic script. They demonstrate, in miniature, how order and rhythm might arise from the timeless equations of quantum gravity. The arsenal grows. Pulsar timing arrays extend the reach of gravitational wave astronomy across decades. CMB's 4 and Light-Bayard promise sharper images of polarization. LISA and its successors will trace waves millions of kilometers long. Hypercameo Condi will watch the universe's ghostly particles. Euclid, Roman, Rubin will map billions of galaxies. CERN and future colliders will measure the Higgs with new precision. Laboratories will probe vacuums, condensates, and analogues. Supercomputers will simulate. Quantum networks will entangle. Each is a different kind of dial, each tuned to a different frequency of the possible clock. The effort is not only technical, it is philosophical, for the very act of testing assumes the clock exists. To search for primordial oscillations, for gravitational echoes, for patterns in galaxies, is to wager that creation is not singular but structured, not arbitrary but rhythmic. It is to assume that before the first light, something already pulsed. This wager may be proved wrong, but if it is proved right, then humanity will have detected not just the remnants of the Big Bang, but the cadence of what came before. Thus, the scientific frontier gathers around a paradox. The most advanced instruments of the 21st century are aimed not at what is, but at what may have been before is began. The goal is audacious, to detect a tick in silence, to find a rhythm in what by definition predates time, and yet with each passing year, the arsenal grows sharper, the data richer, the simulations finer. The universe waits. Whether the oldest clock beats in the oscillations of inflation, in the cycles of eons, in the discreteness of spin networks, or in the entanglement of holographic boundaries, its rhythm may yet be heard. Humanity has stretched machines to their limits for this single purpose, to place an ear to creation and listen. In the end, the question of the clock older than creation is not merely scientific. It is existential, poetic, almost theological. To imagine such a clock is to confront the nature of time itself, and with it, the essence of existence. For if time predates the universe, then the universe is not the origin, but a moment one tick in an older rhythm. The night sky becomes a meditation on this idea. Each star is a burning clock of its own, counting down the seconds until its fuel is spent. Galaxies rotate like vast gears in a machine that no one built. Black holes, paradoxically timeless, may conceal the very equations that hide the deeper metronome. Even the expansion of the universe, steady and accelerating, behaves like a constant beat, a reminder that something persists beneath the shifting stage. Human beings have always measured time by motion. Sundials, water clocks, mechanical gears, atomic oscillations is more precise than the last. Yet all remain fragile, temporary, subject to decay. The cosmos, however, suggests the possibility of a timekeeping that does not rely on hands or pendulums, but on structure itself, the stretching of space, the vibrations of fields, the birth and death of universes. Compared to this, human clocks are sketches against eternity. This realization brings both humility and wonder. If a clock older than creation exists, then the human sense of beginnings and endings may be misplaced. What we call the Big Bang may have been only one transition, a single chime in an infinite sequence. Our universe might not be a story with a first page, but a chapter in a book without beginning or end. Roger Penrose's vision of conformal cyclic cosmology imagines exactly this. Universes following one another like waves on an infinite sea. The faint circles he claims to see in the microwave background are not just anomalies, they are fossils from a previous eon. Scars left by black holes evaporating in an older cosmos. If true, then our sky carries the memory of a universe long gone. The face of the clock is etched into the very fabric of heaven. Others imagine a different rhythm. In loop quantum gravity, time itself dissolves into discrete quanta, indivisible. Moments that tick like Planck-sized heartbeats. Reality becomes granular, not continuous. In this picture, the Big Bang is not the beginning, but the transition from one arrangement of quanta to another. The clock has always been ticking, in intervals too small for ordinary perception. String theorists go further still. In the curled-up dimensions of their equations, hidden oscillations may thrum eternally. These vibrations could predate our universe, and perhaps every universe. They could be the ultimate clock, not tied to stars or space, but woven into the symphony of existence itself. Philosophy cannot ignore these speculations. If time is deeper than creation, then what of causality? What of beginnings? The arrow of time, the one that pulls all life toward entropy, may itself be local, a feature of this universe only. If there is a clock older than creation, then causality is not universal, but emergent. Beyond creation, there may be no before and after, no chain of cause and effect on the rhythm. Only oscillation, only recurrence. For humanity, this is both unsettling and liberating. Unsettling, because it strips away the comfort of a singular origin. Liberating, because it suggests continuity beyond death, beyond endings, beyond collapse. If universes rise and fall like tides, then perhaps existence itself is never annihilated, only reshaped. The clock does not stop, it simply strikes a new hour. And yet, a paradox remains. If the clock is older than creation, then what is it measuring? Time itself? Or something deeper, something more abstract, like information, entropy, or possibility? Perhaps the word clock is only a metaphor, a human attempt to grasp something alien. In truth, the universe may not measure time at all, but pattern. The rhythm may be one of symmetry, breaking, of transitions between states, of eternities collapsing into moments and moments swelling into eternity. Here lies the philosophical core. Perhaps time is not a line, not even a cycle, but a tapestry. Each thread is a tick, woven through others, with no single origin point. The Big Bang is then not the beginning, but a crossing of threads, a place where the weave became visible to itself, for the human mind. Raised on clocks and calendars, this is almost incomprehensible, yet it touches something profound. It suggests that beginnings are illusions, that ends are transitions, and that existence itself may be older than any creation story. And so the night sky takes on a new meaning. Stars are no longer just distant fires, but luminous markers of a deeper cadence. Galaxies are not only structures, but arrangements within a larger harmony. The cosmic microwave background is not simply an afterglow, but a page torn from a much older manuscript. The silence between the stars is not absence, but pause the rest between beats of a clock that has no maker and no end. In this vision, humanity's role shifts. We are no longer inhabitants of the first universe, nor custodians of the last. We are witnesses within a chain, part of a rhythm so vast that no single lifetime, no single civilization can encompass it. Yet by noticing it, by straining up instruments to hear the faintest oscillations, by imagining the possibility of clocks older than creation, we participate in it. We become part of the rhythm, aware of its existence. This awareness changes the meaning of mortality. A human life is short, a flicker measured against eons. Yet within that flicker lies perception, imagination, the ability to glimpse the eternal. Clock, that glimpse does not abolish death, but it reframes it. If existence is cyclical, if universes rise and fall, then death is not silence, but transformation. The clock does not stop. It ticks on, and so do we, though not in forms we can. Now, imagine, the final reflection is quiet. Perhaps the clock older than creation is not out there in the sky, hidden in gravitational waves or etched in cosmic microwave maps. Perhaps it is already here, in the persistence of memory, in the laws that do not change, in the fact that mathematics describes reality at all. The rhythm may be embedded in the very possibility of order. Thus the story closes, not with certainty, but with humility. The cosmos may indeed carry a hidden rhythm, older than any beginning, deeper than any end. To search for it is to confront the mystery of time, and in so doing, to glimpse something infinite. The last image is of a pendulum swinging in silence. Not a human pendulum of brass and weight, but a cosmic one, invisible, ungraspable, marking. Moments before there were moments, beating before there was being. The clock older than creation ticks on, indifferent to beginnings, indifferent to endings, eternal in its silence, and humanity, fragile and brief, listens.